So can everybody hear me okay? In the back, yes? Okay. So I have to start with a little confession. So I'm not a statistician. I'm actually a computer scientist. And even as a computer scientist, while I publish in a lot of machine learning venues, ICML, NIPS, AI stats, and I've been a co-chair, I'm actually more AI person, and I do some work in databases. So this talk will be a little bit different. I hope that you'll have patience with me. There's going to be different language and so on. But you know, I figure a talk this late in the day, I'm going to try and do this at a kind of high level, maybe give some ideas, some places where there's opportunity for cross-fertilization. But I do want to reassure you guys, if I were a statistician, I would be a Bayesian statistician. So, all right, so the world that we live in, the kinds of places that we want to apply statistical modeling, predictions, causal modeling, and so on, we're dealing with data that is multimodal, multi-relational, different kinds of entities. There's interesting spatio-temporal relationships. And at an abstract level, oftentimes what we do, and by we, I don't mean you, because you are the few that don't do this, but a lot of what machine learning people do is they take this nice, richly structured graph, and then they flatten it, and they put it in a table. And usually when they put it in a table, you can think of each of these rows as representing nodes. So they've defined the units in a particular way where the units are associated with nodes. Occasionally, the units are associated with edges, but what I'm going to be arguing for and showing in this talk is a way of kind of slicing and dicing this that's a little bit richer and which can obey some of the kind of structure that is inherent possibly in your data. And then I hope that we can then make a lot of connections between the kinds of models that have been talked about today already. So the challenge is, again, still kind of wearing the computer scientist hat, is much of the work in statistical machine learning makes this horribly incorrect, you know, IID assumption about the data, and you know, from a graph perspective, thinking of it as these nodes. Then there actually is an older line of work in the machine learning community, kind of before they discovered statistics, where they were thinking very much in the combinatorial hat. So it was much more about logical descriptions of the data and being able to talk about, you know, does this description cover these things? And the advantage of this work is that it did have a nice language for talking about the structure in the data. But real-world data sets, we know, don't obey this property. So there is a community that has been working since the like 2000 or so, where it mixes both the kind of rich representations that one uses from programming languages, from databases, from logic, from knowledge representation with statistical modeling techniques. There's been a series of workshops, dog stool meetings, and so on. And I'm not going to go into a deep dive about this community, but if you're interested in kind of seeing the flavor of the models that they use, there's a NIPS tutorial here which kind of goes into a lot more detail. Let me, especially, you know, for this audience who I doubt is familiar with any of this work, try and give you a caricature of some of the work. And this is based on the kind of a line of work that my group has done over the years, where the first set of work was probabilistic relational models. This was late 90s, early 2000, where very much it was based on graphical models. So in particular, these ones are based on directed graphical models, but then adds into the representation a way of talking about the random variables, so that you could talk about random variables that are either the kind of attributes of nodes, if you will, or the edges. So you would have random variables which would represent whether or not an edge exists. And interestingly enough, around 2001, we had a paper on uncertainty in link structure, and we proposed a bunch of different models, but if you look at them, one of them is suspiciously similar to stochastic block model. So it's kind of interesting that different communities, kind of similar ideas come up as well. Then we also have done, and a number of others have done, work where you have kind of unnormalized conditional distributions, and you're putting these together. I'm going to return to those later when I talk about kind of a challenge problem that I think is interesting for this community to think about. And recently, we've been doing some work on what we call probabilistic soft logic, and that's what I want to give you a taste of here, because one of the things that's nice about this is it is a statistical model that is well suited for these kind of rich graph structures, but it's, and if you will, to kind of put it broadly in a class of models, it's a undirected conditional kind of model. I'll show you in a sec. And the cool thing is it's highly scalable. So let me go illustrate this by cartoon. But first off, it's a probabilistic programming language. I'm going to give some examples in a sec, where we're going to be able to use predicates to represent either the attributes of nodes or the links or edges between them. A key distinguishing aspect of this model in comparison to many of the other models in this space of families is the random variables can be continuous valued between 0 and 1. And I'll get back to why that's important. And then we can have rules, which are the things that will capture the dependencies, and they'll capture the kind of structure of the model. And I won't go into it here, but a big thing that ends up being useful is, when you're talking about a graph, talking about the sets of neighbors and so on, so there's a nice language for doing that. And then a PSL program, it turns out, is going to be these rules together with an input database, which you think of as your evidence, and then that's going to define a probabilistic model. But so what does it look like intuitively, and what are some of the kind of common kinds of inferences that we want to make? Well, one of the simplest is trying to predict labels for nodes. And so in this example, I'm sorry, this is US-centric. I should have adjusted this. But the idea is we have an individual, and we're trying to predict their political persuasion. And so, of course, we can use kind of basic information about, what campaign they contribute to, and, if they contribute to a particular campaign, then it means they're more likely to vote. And so this is an example of the logical language. So you're able to express these covariates in this kind of nice way. And then I'm going to tell you how these weights are interpreted. These are the parameters of the model. These are the things that you're going to end up wanting to learn from data. You can also use things like information about what they post, And you can have statements that talk about, if they mention a particular loaded keyword, then that may mean they're more likely to vote for a particular party. But that's all well and good. That's thinking of it as a node in isolation. The interesting thing is to think about it in the network setting, where the network setting, I'm going to make use of the relationships to model dependencies. And so the kinds of dependencies that I can model are things like if their friend votes for a particular party, they're more likely to vote for a party, or something that maybe happens to have a stronger dependence. If their spouse votes for a party, they're more likely to vote for a party. But really what I want to do typically is that I'm going to have some of the labels observed, and these could be observed with some confidence, or they could just be, we're going to say we know these labels, and then I want to be able to infer jointly the missing labels. And so how do I take into account all of the kind of correlations and dependencies in doing that? And so that's one problem for doing node labeling. The other kind of problem that we often do in these is predicting edges, essentially. And again, let me illustrate this with a little cartoon example. So this is a little bit richer because I'm going to have communications, and then I'm going to infer the kind of communication, and then based on the kind of communication, I'm going to infer the kind of relationship. So I can say, if someone sends a deadline email, or sends an email that has due in it, then it's a deadline email. Maybe they're social emails. Then I say, if someone sends deadline emails to someone, they're more likely to be in a supervisor relationship. And then finally, you can have these kind of definitional things that say, if A is the supervisor of B and A is the supervisor of C, then they're colleagues, or some sort of transitive closure or something like that. Those are easy to encode. So what's going back to PSL, the key element are these weighted rules. And the weights are the parameters of the model. And these rules are going to be instantiated according to the input database. So they'll be instantiated multiple times. And now if you go back to combinatorics or logic and think about these as logical variables, this is well known to be intractable for finding the max weight of the unknown variables. What we do in PSL, and what is really cool and makes this tractable, is we're going to convert this into a convex function. And the way that we do this, to me, the really interesting mathematical thing, which I'm not going to go into detail here, is we can use 3 different interpretations for the semantics of the random variables and end up getting to the same optimization problem. The first one that we did was actually using a form of co-norm and t-norm that comes from soft logic, and this was in the interpretation where we want to say those random variables are degrees of truth. Interestingly, it turns out that this is the same as if you have an interpretation for the probabilities as expectations, and expectations for rounding probabilities, the probability that you'll round up to 1 or down to 0. So we can make use of LP guarantee that is nice because it actually gives an approximation guarantee. And then the third thing that we connected to is actually pseudo-marginal relaxations for Markov random fields. This is something that's very, very, very popular in the graphical models community. So even irrespective of what we're doing, the fact of making this connection between this relaxation and this LP program with approximation guarantees is interesting. But given this is a short talk, the key structure of the optimization is basically it's a conditional random field where we have the y is conditioned on x's, but then the rules come in to these loss functions, and the loss functions, and the reason we call them in the end hinge loss Markov random fields, have this kind of flat region where the rule is satisfied, and then a straight region for which they're dissatisfied. And all of this allows us to construct this log concave construct, and then doing the map inference, so for y's, ends up being very fast. And so you can just throw it into interior point method, convex solver, or you can make it even faster by making use of popular methods in the optimization community right now. This is seeing a resurgence where the idea here is basically you have this large optimization problem, but it has a huge amount of local structure in it. And this local structure comes from these rules being repeated multiple places. So what you can do is you solve each of the local optimizations, you take their solutions, you average them, you pass that information back to problems, resolve it. This turns out to be guaranteed to converge for convex problems. And the cool thing is, even on a medium-sized problem where you have 500,000 potentials, using the standard optimization technique would take over an hour. Using this, you can solve it in like 2 minutes. So what do PSL programs look like? This is actually an example of the PSL program for the collective classification problem. This is an example for the link prediction problem. And, we really have a lot of others that we've done. So we've done them starting off with some comparisons. This is a comparison of both a node labeling problem, and this is a kind of ranking kind of problem, comparing PSL, or hinge loss Markov random fields, with discrete Markov random fields. And you see this is accuracy. We're doing a little bit better in accuracy, and this is area under the precision recall curve. We're doing a little bit better there. But the key thing is the difference in speeds. Again, these are relatively small problems, but we're doing them well, and we're doing them fast. Compared to image completion task, this is one where it actually really gets the benefit of the fact that we have random variables between 0 and 1. We're comparing with deep networks, PCA, and so on, and we're doing very well in terms of comparing to state of the art. This was actually a best paper a couple of years ago, and we're also able to do it fast. Another flavor of computer vision problem is an activity recognition problem. Here we can use state-of-the-art computer vision features. This is histogram of gradients, and I forget what ACD is, but then use PSL as exactly the thing that kind of connects the dependencies between, okay, if I'm doing something in one frame of the video, I'm likely to continue doing it. If there's other people in the video and they're doing something, then they're likely to be doing the same thing. None of these are hard constraints, but we can add them in and that improves performance significantly. And then on drug target prediction, again, we can compare to state of the art, and we're able to beat it. And using PSL kind of as the fusion that fuses together a bunch of existing techniques and models of dependencies. So we have also done this in a bunch of computational social science problems and information integration problems, including hybrid recommender systems. And just to give the kind of PSL in a slide, map inference is really fast, so this can be something that goes into a bigger problem. We can make it faster with state-of-the-art optimization techniques. It outperforms discrete MRFs, both in speed and accuracy. I haven't talked about it, but there's methods for learning the weights and latent variables. And the thing that is so far the most Bayesian that we've done with these is we've used PSL as a structured prior as input to a latent topic model. And so this is a way that you can kind of condition on all kinds of rich co-author information and other kinds of network information and make things scalable. There's lots of applications, and it's open source. We have tutorials and so on online. So popping it up for discussion, I want to pose a problem which I find very compelling. And I call it graph identification. You guys probably call it something else in your community. But it's this idea of I have some observational network, and you can't really see this, but this is an email communication network. And what I would like to do is kind of solve the inverse problem of saying, okay, what's the underlying social network, or what's the underlying organization hierarchy that led to this? So I have this as input, and what I would like to do is, first off, solve the challenge of the fact that, while I have nodes that are observed in this one network, they correspond, there are multiple observations from the underlying network. So I want to map the email addresses to nodes in the graph. And so this generally goes by the name of entity resolution. In some parts of the community it has a bunch of other names. But this mapping nodes to underlying units maybe is the right language, I'm not sure. Then I want to infer the actual relationship. So I have communications that I've observed, but I want to infer what are the relationships between the individuals, who reports to who are friends, and so on. And then finally, I want to label the nodes. And so maybe it's labeling them according to their role in the organization, whether or not they're a manager, the CEO, and so on. And so trying to put together all of these inference tasks at once is, they're very intra and interdependent. So what is the right way to formulate this? What's the right way to deal with the uncertainties? We have had some success at doing this using these kind of coupled conditional classifiers, but it would be much more satisfying to have a better theory for this. So I think there's a lot of opportunities. One of the big places is my interpretation for what we're doing when we're coming up with these logical rules is that we're basically figuring out what units to create in this large richly structured data. And so we're deciding how we're going to slice and dice and parameterize things. And so what does that mean in terms of, can you say anything then about exchangeability, given the fact that you've decided to slice and dice things in this way? The other piece is, I said that we had these different semantics. What I would really like to do is come up with a Bayesian interpretation for it. And so I have intuition, but it really is, unfortunately, only an intuition that, there's something about the fact that I am able to represent these things as degree of truth. And then there is something about the fact that I can represent things in a statistical way in terms of these rounding probabilities. But what's the proper way to kind of put these things together? And then finally, how do we solve the graph identification problem? And in particular, how do we solve it in a Bayesian way? Because clearly you don't want to have something where you just have, here's the most probable graph, but you want to have some sort of characterization of the uncertainty. Thanks.
In the middle, you were talking about things that were sounding a lot like deep learning neural networks. Can you comment more explicitly on the relationship there?
Yeah, so there's a place where the fact that we've parameterized things in the way that we have, in the case where we don't have latent variables, what we're doing is a highly, highly efficient way of doing inference in these kinds of models. Particularly with the current rage in deep networks and so on, their advantage is they're able to take things that are very unstructured and exploit them. I think our advantage is at the other end of the spectrum, where if you already have structure in your data, if you already have a database, don't flatten it and make me figure it out again. Use that in the structure of how you specify your model and how you parameterize them. On the other hand, wearing my AI hat, I think there's an opportunity for both of these things to come together. So on one hand, you make use of whatever domain expertise you have about representing, what things are entities and what things are relationships. And then at the same time, you do your unstructured discovery and then put those together. So.
Follow up to clarify. I got confused about what you learn and what you postulate a little bit. So you learn the weights of the rules, right?
In this, yes, you learn the weights of the rules.
And all the rules are postulated from domain knowledge, is that right?
So in what we've done so far, there actually is a whole family of techniques for learning the structure of the rules, and so that it is very possible to learn the structure of the rules at the same time.
Is there anything else you have to learn on top of the weights of the rules, or it's just then you combine the rules with the weights?
In the vanilla setting, no. Yeah.
Do the structures that you end up with, you argue that they're fast and that you can get them quickly and that you can get predictive power. Do you get any insight into structure? I mean, sort of what factors are important, what things interact the most, and so on?
So you do, but you have to take some care to not overinterpret the structure that you get. So, for example, oftentimes we show these models to domain scientists and they put an interpretation that, like, they think that the rules are causal in some way. They're not by any stretch. So I think it does provide insight, but one needs to take some care. And I would be very interested in being able to do more forms of kind of model comparison and so on. I think that that's useful.
I also have a question about the rules. There is obviously a trade-off between the discovery and kind of exploitation. So how does it manifest in this setting?
In this setting, because I'm not getting to the...
Well, in terms of rules, so even if you have preset rules, so there are kind of two opportunities to invest time into learning the weights of different rules, or just try to take some ad hoc weights and try to establish something. Also, it's possible just to do, first of all, take some ad hoc weights and quickly do analysis and then improve.
Yeah, so this stuff, we have not looked at it from that framing. That would be super interesting, though.